Good morning, fancy meat computers. How's everybody doing today? We are back. We are back from break. Everybody's back. Everybody's back. Back, back, back. Back, streets, back. Do. Cool. So, let me check my announcements feed. So, it was kind of terrible because I received, like, very important information, after our last class. Like, our last class before the break was on the Thursday, and I received some very important information on the Friday, which I hope everybody has, at this point, come to understand and realize. So I'll just go over it briefly for you guys, even though this is now expired information. I hope that you saw it over the break. But essentially, the university is mandating a certain degree of vaccination among people who are currently engaged in on-campus activities at any of either the main campus or any of the satellite campuses. So if you don't have your vaccine proof uploaded, the deadline for that was actually yesterday. So essentially, the consequence of this, of not getting the vaccination proof uploaded, is, and I hope you're not hearing about this from me for the first time right now, but the consequence of that, the university went around and took a survey of the professors to determine whether they thought their courses could be offered exclusively online or whether the in-person component was required. And if the in-person component was required and sufficient proof of vaccination had not been uploaded to the MacCheck system, my understanding is that students were going to be unenrolled from any courses which have a required in-person component. I'm not clear about whether or not the university was going to offer refunds to people on that basis. I suspect that it is past the ad drop date. It might not be past the ad drop date, but, you know, the likelihood of getting your money back at this point would be pretty slim, I think. So, there's also been some debate as to whether it's, you know, did you just have to have it uploaded by that point, or did you also have to have it uploaded and, you know, certified by that point? My word to people 2 weeks ago was make sure it's certified, because, you know, it's the kind of situation where you don't want to be caught with your pants down. Let's just say that the way that things seem to be going with this type of policy is that we do not, let's just say that there's not an overabundance of the milk of human kindness that's being mixed into these policies. So I wouldn't expect reasonable exceptions on reasonable person grounds. Let's put it that way. Get your paperwork in order or else, essentially. That's what my advice to people was 2 weeks ago. Whether or not that's actually the university's policy, I believe it to be a prudent course of action. So if if your authorization is still pending, if you have submitted your documents and your authorization is still pending, I would, if I were you at this point, check to make sure you haven't been unenrolled from any of your courses, because that should be happening, yeah, today, I think. They're probably just going to go through it with a script and you know, unenroll anybody enrolled in the wrong type of course. So I would go through. If you're still pending authorization, I would start rattling some cages with the school bureaucracy to get that authorization through ASAP. Yeah. So a couple of comments. Avery says, I've uploaded my proof 4 times, and they said as long as you follow the guidelines, you'll be okay. Mine's stuck on pending review. Yeah. It's taking them a while to approve the submissions. Just let them know yours is uploading and pending. Yep. Yep. I just, to me, the thing that I'm trying to do is, I do think it's prudent at this point in time to not be entirely trustful of this process. I'm choosing my words very carefully here. Put it to you this way. 3 to 4 months ago, there was nothing but denial that anything like this would be required, and now we have it happening right now, and who the heck knows the direction in which these policies are going to be led. I can tell you, though, that, from my personal observations of the direction that the federal and provincial governments seem to be taking these types of policies, I don't think they're becoming more merciful as time goes on, so my advice would be to get your documentation in order. So, anyway. Also, I think we may not have talked about the fact that the exam, I've set a date for the exam, so that is going to be December 20th. It'll be a 24-hour take-home test, just like the test. It'll be open book. If you have a conflict on this day, there are 2 people in the class that have a conflict on this day. So, if you have not already gotten into contact with me, please do so. And I think that's everything. So, they approved yours right after you emailed them. Yeah, so that's the way that this kind of stuff works now, is as they say, the squeaky wheel gets the grease. And that's, especially for those of you who are new to the jurisdiction, that tends to be the way that things work in Ontario in general, is you'll be put in a queue, and then if you make enough of a fuss, they'll process your paperwork faster. That tends to be how things work in Ontario. So, I've made David paranoid. It's like, well, see, the thing about paranoia, right? Under normal circumstances, paranoia isn't a great survival strategy. But every once in a while, people are out to get you. And if that's the case, being paranoid is actually a prudent survival strategy. So there you go. Yeah. Yeah. So, anyway. Enough said on that topic. So, so let's talk about C programming. So last time we were speaking, we were talking about the shell sort algorithm. Shell sort is a cool one. I'm just going to start from the beginning of the section because I imagine you guys remember about as much about where we were with this as I do. I just remember we were doing shell sort. not too far into it. So, you'll remember that we were talking about insertion sort and bubble sort, right? Bubble sort, very easy. The easiest sorting algorithm. You just examine each one of these possible pairs, and you have the higher numbers bubble up through the array as you process it. Insertion sort is a bit of a different algorithm. You maintain a sorted section at the beginning of the array that you build up through examination and sorting, and on every round you examine the next adjacent element to the sorted section, find its correct position within the sorted section, and then move on to the next one. That's insertion sort. Shell sort is it's fairly different. So the main observation that we were building up through our analysis of bubble sort and insertion sort is that insertion sort is more efficient than bubble sort because it contains fewer redundant examinations. The problem, however, with insertion sort is not that much better than bubble sort, despite having a very good best case runtime. It's not that much better than bubble sort because it can only eliminate 1 degree of disorder per swap operation, right? So every time you're swapping things in either insertion sort or in bubble sort, you are swapping things that are already adjacent to each other. This means that you're only reducing disorder one step at a time, right? If you think of the amount of disorder in an array as being the number of space 1 swaps that you would have to do to sort the array under an algorithm like bubble sort, it would be very cool if we had an algorithm that could reduce more than one step, if we could essentially do multiple of these swaps at once and do that usefully, that would be a much better sorting algorithm. Which brings us, of course, to shell sort. Shell is a person, and it's not like a turtle shell. That's not the idea here. A shell, it's a person's name. That's not mnemonic on the how the algorithm works. So, although insertion sort is an improvement over bubble sort, the number of swap operations that must be performed has not changed. This is because each swap addresses 1 unit of disorder. It may be possible to increase our efficiency by performing swaps between array elements that are not adjacent. In shell sort, we extract a subarray, sort it, and then put it back. By selecting elements that are positionally distant, we can reduce large amounts of disorder quickly. Shell sort is often used in embedded systems applications. So the reason that this is a popular one for embedded systems, which incidentally is something that you guys should be interested in as mechatronics people / people in the EngPhys department with a focus on embedded systems design, is it's all to do with memory. So in the early days of computing, memory was the expensive thing, like operating memory. You would have RAM chips in like a compact Presario, like a 486 or something. You would have memory allocated in kilobytes, right? You would have kilobytes, maybe megabytes of memory available to you, as opposed to the gigabytes of memory that we currently have available. So, with embedded systems, memory costs money. Everything costs money, right? When you're designing an embedded system, and especially if you're designing an embedded system for production scale, you want to snap off everything on that system that's redundant, right? Because anything that you keep in there that's redundant, that's not specifically related to device failure, because sometimes you want sometimes you want redundancy in the case of device failure, like if one circuit fails, you could have another one pick up the slack or something like that. assuming you're not doing anything like that, you want to have no more in that embedded system than it requires to operate, and that includes memory. So this is the reason that embedded systems will often not have operating systems, right? Because operating systems require memory and processing power, and if you can bump your system down to using a cheaper controller, for your production run of like 10 million units or whatever it is, you can be saving your company millions of dollars, maybe even tens of millions of dollars, right? So memory minimization is a real concern in the embedded systems domain. Shell sort is a very good sorting algorithm for embedded systems because it's memory minimal. It does not require a great deal of memory to perform a shell sort. And in fact, the code that you, like, the algorithm itself, because that's another thing that you have to keep in mind when you're talking about memory, is that we are dealing with stored program computers, right? So the program itself requires memory, so the shorter you can make the program, the less hardware you need to fit that program on, so minimizing the actual size of the program is also a concern in the embedded systems design at the high end of it. So shell sort is often used in embedded system applications because the code to implement shell sort is small, it is memory efficient, and it does not use the call stack. So if you're, we've talked about the call stack. Using a call stack, like using something, doing a recursive algorithm will use the call stack, right? And using the call stack takes a lot more memory than if you can just do something with pointers, right? And or even indexing. So the key to shell sort is knowing how to break the array down into subarrays. Subarrays are formed by taking an element, skipping h elements, and then taking the next element, and so on until the end of the array is reached. I believe there's a mismatch between the way that I've described this here and the way that it is described in the Wikipedia article. I believe in the Wikipedia article it describes taking every ith element, right? So if you have a gap of h, that means you're taking every h element. So you would take like the 5th, the 10th, the 15th. Whereas the way it's described in these slides is you leave a gap of 5, so it would be the the first element, the 6th element, the 12th element. You would skip 5 and then you would take the next one. It doesn't really matter too much. Like the algorithm doesn't change very much as a consequence of this difference. It's like you're either taking it as h or h plus 1 via the Wikipedia definition. But anyway, so basically, you take your array and you skip n elements, and then you take an element, and then you skip n elements, and then you take another element, and that composes a sub-array. So I've got a diagram here. So if we take our h gap as being 5 on an array of 12 elements, we have 0, we skip 5 elements, we take 6. So our final array is 0, 6. We then start at the next one, right? We start at 1. And then we take that, we skip 5, we take the 7, right? And then we go back to the beginning, start at the next one, etc., etc., etc. So another way to visualize this, another way to think about what we're doing here is it's like taking a one-dimensional array and turning it into a two-dimensional array and then reading the columns, right? So if you break this array up into smaller arrays, each one containing h plus 1 elements, and then just sort of stack them below each other and take the columns, that's another way of taking the subarrays. So the particular sequence of H values varies by implementation. So one of the interesting things about shell sort is that it becomes a very different algorithm with actual different runtime characteristics depending on the sequence of H gaps that you encode into the algorithm. So different researchers have proposed them at different times, most recently 20 years ago. And I'm going to answer that question once I'm finished this, okay? So the most recently discovered efficient series of H gaps is 1, 4, 10, 23, 57, 132, 301, 701. This order has been experimentally derived. So, like most of the through most of sort of H gap research, there have been there's a series of papers going back historically all the way back to the 60s on the H gaps of shell sort, right? And the for most of these things, they derived some kind of formula because they wanted to generate a sequence of H gaps using a formula so that you could get an infinite number, right? You could get as many H gaps as you want. It makes sense to do it as a formula, but the most efficient one was derived experimentally, so no formula was required to derive this sequence of H gaps, and the H gaps themselves do not conform to any known formula. So if you can figure out what the next number in this sequence is, you could write a paper. But actually, though, so, yeah, this order is experimentally derived. No equation has yet been discovered which can predict the next number in the sequence, which means that if you discover it, then you get your name in every textbook on sorting theory. The worst case performance of this sequence is currently unknown. Its best case is pretty good, though. So, if we want... So we did H-gap visualization of an H-gap of 5. If you take an H-gap of... Oh, yeah, question. So, in reality, the array wouldn't already be sorted. Yes, I have... For this example, I've taken this array and I've given each element in the array its index number in order to facilitate the sort of numerological consistency of the example, right? But yeah, normally you would have an array of random numbers. That's generally, like, if the array was already sorted and we knew that, then there would be no reason to do a sorting algorithm. So, if we have an H-gap of 3, we take 0, skip 3, take 4, skip 3, take 8, skip 3. If you sort of chunk this up into sub-arrays, which, basically every element up to the second element, if you consider this a sub-array, it contains one element. It contains the first element of every sub-array that you're trying to generate, right? So if you stack these in the bottom, read it vertically, then you get your sub-arrays. There you go. So the idea here is that we take these sub-arrays and we sort them using a different sorting algorithm. We often use insertion sort for this, and then we pop it back in. So, would this experimentally derived sequence of H-gaps make it most efficient conforming to your definition of H-gaps or Wikipedia's? Wikipedia's, I think. Yeah. I should just change this to reflect Wikipedia's, but, I forgot, and now it's the lecture, and I can't fix it while I'm doing the lecture. I'll go back and fix it. I'll put it on my list. I'll put it on my list. I know that doesn't help us this morning, but This was like a... I'm remembering this problem from last year. So... What kind of sorting is done after the original subarrays are popped back in? So, I have a whole demonstration of this on the next 2 slides, which will hopefully illustrate that. So I'll just leave that for the next 5 minutes. I'll just finish this slide first. So, once we have our subarrays established, we perform insertion sort on each one of them, and then put the elements back into the original array. You don't actually have to declare a separate, like a subarray. You don't have to allocate any memory to perform these swaps aside from the swap space. But as the visual metaphor goes, it's often useful to declare that extra memory so that you can sort it out in your brain a little better. Once all the subarrays have been sorted and replaced for one h value, we say that array is h sorted. The success of shell sort hinges on the fact that smaller h sortings do not disorder larger ones. So this is the observation that makes shell sort work. If you sort among 7s, and then you sort among 3s, the ordering that was produced by sorting among 7s is not disrupted by the smaller sort. So, for example, if an array is 40 sorted and we 14 sort it, the finished array is still 40 sorted. That's just a mathematical property of sorting. As long as the last h value is 0, which is just insertion sort, the array is guaranteed to be sorted. So, question: how can shell sort use very little memory when it also needs insertion sort to work properly? Well, the answer to that question is that insertion sort is also a very small algorithm. And bubble sort and insertion sort are both, in terms of memory, they're highly efficient, right? The thing about both bubble sort and insertion sort do not require you to declare any memory outside of the array itself, aside from one element that you used as swap space, right? You need one element's worth of swap space, but that's all the extra memory you need to designate. And bubble sort is a very, very small algorithm in terms of code footprint, right? It's just a double. It's just a double nested loop with an if statement and a swap, right? Insertion sort is just like a slightly rearranged version of that. It's still sort of double loop based. The thing we're trying to correct here, the thing that we're trying to optimize, is for speed, right? If you wanted to minimize from memory, then you would, ultimate minimization for memory, you would go with bubble sort, because it uses the least memory, because it also contains the fewest instructions. But if speed is also something that you need, shell sort is like a very good optimization point between speed and memory. It uses, in comparison to the other fast algorithms, it's very memory efficient. But in comparison to the very simple sorting algorithms, it uses a little bit more memory. That's correct. But one of its primary advantages is still memory efficiency, because if you compare it to any of the other good sorting algorithms, like quicksort, for example, or library sort, it is the most memory efficient of the good sorting algorithms. So yeah. So essentially, as long as the last run has an h gap of 0, that is to say, as long as shell sort with an h gap of 0 is is just the subsort, which is insertion sort in this case. So let's take a look at how shell sort works. So there. Oh, that's just a little cut off. Sorry. So let's sort our traditional array that we've been sorting this whole time. David says, so shell sort is faster than insertion sort, even though it uses insertion sort. Yes. That's the, yes. That is the whole thing. That's the reason that it exists. Yes, 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 yes. So the thing about, and we'll see why as we examine this this flow, this diagram. So let's do an H2. Let's do an H2 sort, then an H1 sort, then an H0 sort. Okay. So we have our first subarray here. It will be 9, 1, 6, right? Via insertion sort, we get 1, 6, 9 in 2 swaps, 3 examinations, right? We take a look at the next one, 4, 7. 4, 7 is already in the correct order, so 1 examination, 0 swaps. We then take a look at the next one, 7, 3. 7, 3 is in the wrong order, so by insertion sort, we get 3, 7. 1 swap, 1 examination. Now, the observant of you may have noticed that after only the H2 sort, we are now actually, it's now sorted, right? Now, this has to do, now this is kind of a funny result because, you know, I didn't randomly generate that array when I didn't use a random number generator when I produced this example. It turns out that my silly human brain only introduced disorder of an H2 gap here, right? Which is just kind of an interesting result that after the H2 sort, the thing is perfectly sorted, right? So past this point, we have 0 swaps and 3 examinations to do our, we're beginning our H1 sort, right? This label is attached to this arrow. So our first H1 gap, our first H gap of 1 array is 1379, 1379. So the reason we're using insertion sort here instead of bubble sort is because insertion sort performs better on pre-sorted arrays. You know, the more sorted the array is, the better insertion sort performs. And as you can see, it's very possible towards the end of this to get mostly sorted arrays. In fact, that's the whole point, is that it's kind of like the shell sort has a heuristic that sets up the array as mostly sorted with respect to the next sort before it begins the next sort. So, insertion sort, 3 examinations, 0 swaps. Next one, 4, 6, 7. 2 examinations, 0 swaps. It's now H1 sorted. We then begin the H0 sort, and of course this is already sorted via insertion sort, 7 examinations, 1 swap. So, in grand total, there we go. The total number of swaps we've managed to get away with here is 4, and the total examinations is 17. Question. So how do you choose the best H-gap for a specific array? You can't know what the best H-gap for a specific array is because that would require you to have too much knowledge of the array before you sort it. You're just going to have to use a good general purpose H-gap sequence and hope for the best. I believe the one that I asked you to use in the assignment is this one. Now, I believe shell sort, I'm not asking you to do shell sort until we do pointers because it's much easier to implement once we know how to use pointers. But eventually you guys will do shell sort for an assignment question. So yeah. given a data structure... Oh, sorry, that's searching. So, remember what it was for insertion sort, right? For insertion sort, we required 13 swap operations. The total number of examinations was 17, right? So for shell sort, the total number of examinations has not increased, but the number of swaps that we have to perform has decreased drastically. We've gone from 13 to 4. This is a much more efficient algorithm. Remember that of the two of these, swaps are the things that take more time. So there you go. So, David asks, for h equals 1, why are they in groups of 4 and 3? I'm just a bit confused because doesn't h mean the size of the group? No. Nope. You have it inverted. So, h gives you the number of elements to skip, right? So, we compose the first h2 array by, we compose the first h1 array by skipping one element, right? We take every other element and we produce an array from it. So if you take a look, like this just happens to be a case where h is like this has been picked particularly, and it just so happens that the size of these arrays happens to be the size of the h gap. If you take a look at this one, we have an h gap of 5, but these are not, these are not arrays of size 5, nor do we have 5 of them, right? The h is just the number of elements to skip when you're composing the array. So, there you go. While the previous slide implies the subarrays are instantiated separately from the original array, this does not need to be the case. I'm glad we cleared that up, because it's probably that's an important one. That's an important point. Shell sort may be performed without allocating new memory beyond the swap space for insertion sort uses, right? You need one memory cell to use as swap space, but aside from that, you don't actually have to allocate any new memory. The worst case analysis for shell sort is highly dependent on the h-gap sequence. Early versions in the 1960s are guaranteed to be no worse than big O of n to the 3 over 2. The best version we have results guaranteed for is guaranteed to be no worse than big O of n to the 4 over 3. So as you can see, that's like the closer that fraction gets to 1, the closer we get to a linear time algorithm. So in its best case, shell sort performs much more closely to a linear time algorithm than to a to an n-squared algorithm like insertion sort or bubble sort. So there you go. So let me just see what time it is. Yeah. Let's talk searching. In order to talk about search algorithms, we should first define them. Given a data structure composed of elements and an element to search for, a search algorithm tests for the presence of the searched for elements in the data structure. The output can be either a true-false value or the index of the searched for element. So this is different. We've talked about sorting. Now we're talking about searching. Searching algorithms may be applied to many diverse types of data structures, but for now we're going to focus on arrays. You can search a tree, for example. So, again, we don't know what is in the array until we look for it. This is essentially, you know Python's in operator? Like 5 in, 1, 2, 3, 4, 5? We're now going to learn how these are actually implemented. So, the most straightforward approach is what's called linear search. Linear search begins at the first element of the array each element is compared to the searched for element. So we have this element we're looking for. We have an array that we're looking for it in, and we just compare every element in the array to see if it's in there. If it's in there, we return true. If we reach the end of the array and we haven't found the thing we're looking for, we return false. So the worst case complexity of linear search is big O of n. That is, it's a linear time algorithm. That is because for each element in the array, you have to do one operation. In the worst case, that is, if you don't find it. Because, of course, if you find it, you can just immediately exit because you found it, right? The average position of the sought-for element is the middle of the array, assuming uniform randomness. Thus, so if you're looking for the success case, right, like the best case scenario for linear search is that the element is the first element you look at, so it's big O of 1. In the average case, if you consider the average position of the element you're looking for to be the middle of the array, that means it would be big O of n divided by 2. But this is still big O of n because we don't care about constants, right? We would abbreviate this division by 2 away, and we would be left with just big O of n. So we have to use linear search if we can't assume anything about the data. In algorithm design, if data has known properties, we can use this information to come up with better algorithms. And this is a huge thing in algorithms design, is like management of the properties of data. Sortedness is a property of data. If the array is sorted, we can search it much more easily than if it wasn't. If the array is sorted, then we can use an algorithm called binary search, an algorithm that has a worst-case complexity of big O log base 2 of n, which is a very efficient algorithm. Rather than looking at each item, binary search narrows the field of search iteratively until the value is found, or not. So, this is how it works. Yes. Let's say we are looking for a value x in the array A. We create two variables to keep track of the search range. So the thing to think about with binary search, the way to conceptualize this, is that you have regions of the array that you know either contain or don't contain the element you're looking for. So the idea is at each step, you are reducing the amount of the array that you know the element can't be, that you are reducing the amount of the array that you know the element must be in if it exists, and increasing that part of the array where you know the element isn't, right? So it's a search space algorithm. You're reducing the search space at every step, eventually reducing it to a search space of 1, at which point you have an element, and it is either that element or it is not. So, create two variables to keep track of the search range. A keeps track of the lower bound, and B keeps track of the upper bound. That's our first step. Next, we have the loop, the main loop. So we examine the number at index m is equal to a plus b over 2. Floor of a plus b over 2, actually, because this is, we can't have fractional indexes of, memory cells are required to be whole integers, and floor just rounds down in all cases. So I've got a question unrelated to this description. For A2 question 5, should you follow the algorithm given by the description or the visualization? They should describe the same thing. Oh, the description reads A equals M, but the visualization reads A M plus 1. Okay, I'll take a look at it. I might have to Might have to do some edits today. I'll take a look. I'll issue a correction. Should there be inconsistency, I'll issue a correction. It's not that I don't trust you. It's just, you know, I gotta look. Oof. Ouch. All right. So, step 1. If the numbers at m, a, or b are equal to x, then we have found x. If this number is less than x, we know that x must be at an index higher than this particular midpoint. Thank you. So this is the key observation, right? We take the middle of the array and we examine it to see if it's greater or less than the number we're looking for. Since the array is sorted, we know that if the element in the middle is less than the thing we're looking for, then nothing that's less than that can be the thing we're looking for either. So we can exclude from our search the entire first half of the array. Conversely, if the element in the middle is higher than the element that we're looking for, we know that everything higher than that can also can be safely excluded from our search. So that's the way that this algorithm goes. So since we know that either the top half or the bottom half of the array must contain the element that we're looking for, we can close the A and B bounds in, right? We can close them in around, we can narrow it up, we can close that interval around just the area we know that to be in. So, yes, if this number is less than x, we know that x must be at a higher index than the midpoint. Therefore, we set a to the midpoint and return to step 2. If this number is greater than x, we know that x must be at a lower index than the midpoint plus 1. So, we set b equal to the midpoint minus 1 and return to step 2. So here is our visualization. So we have this array, which is sorted. A is 0, B is 29, and the midpoint is 14. We're currently looking to see if 84 exists in this array. So I'll just zoom in a little bit for you guys. There we go. So A is 2, B, so this is the lower bound, this is the upper bound. Having a lower and upper bound when it's like the entire array you're searching doesn't make a huge amount of sense, but you know, it's for consistency. So the midpoint here is 14, so the element in the midpoint is 49. X is greater than 49, it's 84. So we know that the element we're looking for must be in the top half of this array. So on the next step, we move this A value up, because we've already tested the midpoint to see if it is exactly equal to the value we're looking for. So we can safely skip it and move to the next one, right? So our A bound becomes, we're searching now from 54 to 97. Our midpoint value becomes 78. So 78 is still less than 84. So we know that the element we're looking for must be above 78 and less than 97. So we move our A bound up again. It becomes 82. Now we examine the midpoint and we get 93. 93 is greater than 82, so we know that our value we're looking for must be in the lower half of the array. So we move this B bound down. We result with 82, so 82 is our lower bound, 84 is our upper bound, and 90 is our 84 is our middle, and 90 is our upper bound. We hit the condition that one of our highlighted numbers is the number we're looking for. So we have found 84. There you go. This visualization says A15 in the second step. But according to the slides, it should it not be A14? So, possibly. I'll take a look at this one too today. Oh my gosh, my book just broke. I hate it when your book breaks on a Monday morning. Yeah. So the idea behind this implementation is that if you've examined, like, if you're testing the A and B bounds for whether or not they're equal to X, you don't need to test them twice, right? So when you move the bound in, you don't need to move it to the midpoint. You can move it one past the midpoint because you will have already tested the midpoint, right? But, you know, I'll double check this to make sure it's consistent. And that's our class. All right. We have a few more slides, but that's, like, I've got like one more slide, but that's okay. We can do that tomorrow. When the midpoint is larger than the X value, we make the new midpoint the smallest value left. No, you make it, you make the lower bound the next one, right? You close the bound in, and then you calculate the new midpoint based on the new bounds. So you should do floor A plus B divided by 2 plus 1 if you're looking up, and minus 1 if you're looking down. Yep. It's just, like, doing it that way gives you, like, the option of an early escape. Can you give an example when the point we're looking for is smaller than the average? Yeah, this one. This third step. In this case, the number we're looking for is 84. And it's, 93 is greater than 84, so we move the upper bound down instead of the lower bound up. Right? It's symmetrical. Good. Any further questions? Okay, well, if there are no further questions, I'll log off here. See you soon, folks.